which group, look at the periodic table, which group typically people use to make semiconductors, right? That's basically what, if you look at this, right, you can think about zinc oxide, right? That's what, that's like a zinc group, and then this is this group, right? And then you have what, the oxide group, that's 2,6, right? 2,6 group. And then you can also, form the semiconductor from, gallium arsenide, right? See, this is zinc oxide, and that's 2,6. And then I use different color. You think about the gallium arsenide, that's what, 3,5 group, 3,5, right? And of course, this group itself, so you have silicon, you have germanium. It can form the semiconductor by itself, and they call that, just, that's a semiconductor. You don't need to form compound. That's a silicon wafer, germanium wafer. That's a semiconductor. Even carbon, right? If you have graphene, graphene is a semiconductor, okay? Graphene can be semiconductor. There are metallic graphene, semiconductor graphene, that's also, obviously. So here, basically what all these four groups are, you can use to form semiconductors. So now let's see the semiconductor materials, right? As we just talked about, right? Group 4, and then group 3, 5, and then group 6, 2, 6, okay? Group 4, 3, 5, and then 2, 6, okay? These are the common semiconductors materials element people use to, grow the semiconductors, okay? And then the semiconductor structures, look at silicon, right? Silicon, you have 4 valence electrons, right? This is, I think all you guys probably know this, very basic, right? 4 valence electrons, and then that's why you form what? 4 covalent bonds, right? 1, 2, 3, 4, right? 5, 6, 7, 8, right? Each of these is 4 bonds, right? Each bond has 2 electrons, right? There's 1 electron from this silicon, another electron from the neighboring silicon, right? See, this is the 1 silicon, this 2 silicon. Each give 1 electron for the covalent bond between them, okay? Since the silicon, form all the covalent bonds, and then some of these bonds can be ionized at room temperatures. That's why, as we discussed yesterday, you have about 10 power 10, per centimeter square cubic, right? Ni, that's called intrinsic free carriers in silicon wafer. There's basically so many activated, free electrons there, okay? So this is very basic structures. And then if you look at, how this electron transport in silicon, right? Now let's see, just in case, for some reason, this electron, this bonding was broken, this electron, moved to the next positions, right? Then you see this, and then again, when it's moved to here, it's become more extra electron, right? And then it can move around, anywhere, And then if you have holes, you have the same thing. If you have the hole here, this hole is basically it's broken bonds, right? Or missing electrons. This can go to this position, and then this position, that position. They can move around migration. You can see they do the migration, or they are decollides. That's how the silicon, even the pure silicons, intrinsic silicon have some kind of connectivity there, okay? And then if you have electric field there, you can, without the without the electric field E, the electron holes will go random directions, right? And then they may come back to the same origin position. But with the electric field, then since this positive, right, this negative, the positive has to go from the right to left, negative has to go from left to right, right? Because there's attraction, right? Electric field attraction for that. So that's help you to have a directed charge transport, or electron transport or hole transport in the silicon wafers, okay? And also there's the other, semiconductors is, that's probably, I did not talk about that, like this compound semiconductors, gallium arsenide, zinc oxide, all these kind of semiconductors. That's we did not discuss here. Then that's okay. I think probably also cadmium tantalite, that's something we'll discuss when we talk about the thin film solid cells in the next few days, okay? So that's about the transporting semiconductors, and then also structure is an important thing. Now, whenever you look at the structure can be what? Can be single crystalline silicon, that's this. You see everywhere the silicon has order structures. It's a long-range order structure. There's almost defect. There's almost no, ground boundaries. Okay, and then you have polycrystalline silicon. Polycrystalline, right? That's basically, you see these regions. There's a silicon, and And then these regions, there's very good single crystalline silicons. But in these regions, you see that's grand boundary. That's why it's called poly. You have more than one, regions in the tiers. And then if you look at this guy, it's called amorphous. That basically there's no, even there's no net crystal structures inside. All the silicon atoms disordered with each other. There's dangling bonds everywhere with each silicon atoms. So that's why you form this amorphous. So you can see you can have crystalline silicon, polycrystalline silicon, amorphous silicon. Okay. And then the silicon structures is very similar with look at the periodic table. You have what? You have carbon, right? You have carbon, you have silicon, you have germanium. Okay. All these group 4, group 4. This silicon crystal, germanium crystal, they take the diamond, diamond structure. The diamond structure basically with the carbon, right? That's what you. Then the silicon take the same structure, germanium take the same structure, as a crystal. So here I do have this, okay, the zinc blend structure. You can see here, have gallium arsenide, indium arsenide, cadmium telluride, cadmium sulfide, gallium nitride, okay? You see all these. So here, this structure is very similar to these diamond structures, right? But here you have the same silicon, same atoms, the one atom, right? But here you have 2 different atoms. It was 3 different atoms. But here, since all these, 2 elements, you have 2 different atoms, okay? So that's only different. But the structure looks similar to that diamond cubic structure. So lexine, it's something it's important, especially for photovoltaic, is called band structure, okay? So the band structure, what you see here is very basic. You have the conduction band, EC. You have valence band called EV. That's energy on the conduction band called, energy for conduction band. That's called EC. And then the gap between them called band gap. Basically, in band gap, there's no energy state. Okay, there's no energy state. And then that's why it's called forbidden gap. There's no electron can stay in the gap. Okay, that's why it's called forbidden. There's no state for the electron. The state is like the chairs in the classroom. When students come to the classroom, you have the chair to sit, right? If there's no chair for the student to sit, they have to stand or they have to get out of the classroom. That's the same thing, right? If the classroom have only 30 seats, that's a capacity. Any more students come in, they cannot even stay in the classroom. That's the same position. The gap, there's no state for the electrons. That electron cannot stay in the gap. Okay. And then the band gap depends how big the band gap. You can see if the band gap is if this EG is between 0.5 to 3 V, you call that semiconductor. Okay. If that's larger than 5 EV, basically call that insulator. And then if the band gap is this is it around 0 or smaller than 0, even negative, and then you call that conductor or metal. Okay, metal. So this is typically for inorganic semiconductors, like silicon, germanium, gallium arsenide, silicon nitride. Silicon nitride probably is the insulator, okay? And the gallium nitride, cadmium sulfide, all this. And then also, as you guys asked a question yesterday about the dye-sensitized solar cell, polymer solar cells, these are organic materials. And then organic material, you call that molecular, semiconductors. And then you call that NUMA, HOMO. NUMA is the lowest unoccupied molecular orbitals. HOMO is the highest occupied molecular orbitals, okay? So, and then here's a few equations here, and then we'll talk about this equation later. So right now it's okay. Okay, this called, mass, you can also call the mass conservation equations. Ni squared equal to N0 P0. That's basically N0 P0. That's Ni is intrinsic, right? N0 P0 is the dopant, or you call that, Sommer equilibrium current density. Okay, that's the current density under Sommer equilibrium. Okay, that N00 P0. That's what it means. And then NCMV is the state density state. The state density of the conduction at the conduction band or state density on the valence band. Okay, and this is this one is sigma I is conductivity for the intrinsic silicon without any doping, right? So since the silicon, you have both electron and holes there, both electron hole has their own mobility. That's why entire conductivity equal to what? Electron conductivity plus the hole conductivity. QNI mu n is electron conductivity. QNI mu p is the hole conductivity. You add them together, that's the total conductivity for the silicon wafer. Okay. So here's the question, what is the band gap in semiconductors, as we just mentioned, right? From 0.5 to 3, right? That's basically what? It's 2.5, okay? So this question, some related question, probably you can figure out by yourself, okay? I'm going to skip this, okay? This is a question for you, you to study. And then the band structure, okay? The band structure we just talked about, you have, EC, EV, and then between them it's called EG. And then depends, what material you are using. If you think about silicon, the band gap is about 1.12. Germanium is 0.66, gallium arsenide is 1.4, cadmium tantalite is 1.4, cadmium cyanide is 1.7. Okay, and then you can see the band gap just increasing, right, as you use different materials. And you can also use cadmium sulfide, tin oxide, zinc oxide, and then you get very close to, large band gap semiconductors. So the semiconductor for PV applications, as we just mentioned, there's inorganic one, typically covalent bonds between them. Some of them may be, ionic bonds, but typically it's covalent bonds, okay? Ionic bonds will hold electrons so strong that you don't have delocalizations. That's why ionic bonds are not, often used. It's very certain, for semiconductors. So, and then organic semiconductors that can be, dyes, porphyrins, right? That's the porphyrins. Okay, and then the polymers, right? And also, if you look at this from the materials point of view, right? Whether you have carbon or you don't have carbon. If you think about structure, right? You can have single crystalline, multi-crystalline, polycrystalline, net-crystalline, and amorphous. That's something we just talked about, right? Then this question, I'm going to skip this, so students, you can study this by yourself, and then you can figure out that. If you have a question, you can ask tomorrow as a tutoring time, right? From 9, right? From 9 to 11 is US time, okay? US Eastern time. So there's one question probably come to your minds that says, what is the best band gap for me to use if I want to fabricate solar cells? What would be the best band gap? Okay, the best band gap, single junction, right? And then you can do simulation, right? The simulation, you figure out that if my band gap change from 0.5, let's say 0.5 to 2.5, okay, and then you can see that my efficiency for different, band gap efficiency will be different. The maximum band gap is somewhere about here. If you look at these regions, you can see that gives you the maximum efficiency. Maximum efficiency. Oh, I'm sorry, not that. Okay, the efficiency basically is these two lines, right? Of this, Oh, I'm sorry, not this. Okay, you can see the efficiency is only one line here because this one is it's called, okay. This is a black body limit. What does that mean? This one is M0. So there are 3 plots here. These are all for efficiency, but what do we really care about? Only this line, M1.5. Because M1.5, that's the light intensity received on Earth's surface, right? And then the M0 their black body limit, that's basically outside the air environment. It's basically in the space. The light intensity is stronger because there's no air to, scattering or absorbs the sunlight. So that sunlight here is about 1353 watt per centimeter square. When you get to M1.5, it will be about 1000 watt per meter square. Okay, that's it. Okay. I don't know why here there's a lot of M0. Okay, so this M0 is let's don't worry about that. Okay, this is the black body limit. That's M0. It's a lot of M0 probably just just above the air. Okay, air atmosphere. But anyway, what we care about is M1.5. This plot. Okay, this plot. Okay, this plot. This plot, the maximum here, as I just mentioned, is this position. See this position, right? This period go down here about 1.4. Okay, 1.4 eV. Okay, about 1.4 eV. That's the maximum. Yeah. Basically, for single junction devices, if you can have 1.4 eV as a band gap, and then that's theoretically you can get the highest efficiency. That's about 25%, 25% efficiency. Okay, that's gallium arsenide. Okay. So what caused the band gap in semiconductors? This probably you guys know this from solid state physics, right? Solid state physics, you have this all this kind of theory there. Okay. Basically, if you have one, think about the semiconductor. If they are crystal, right? The crystal, there's many delocalizations, right? The structure is so organized that the electron can delocalize on many atoms. If the electron stay at one atoms, okay, or one molecules, you have one state, right? Then the two electrons will stay on the ground state. Okay, if you have two electrons, you have two molecules and the two atoms come together and they have two states, right? And then you have n. If you have n molecules come to delocalize, interact with each other, you will form many energy states there. Okay, this one just assume one atom or one molecule have one energy state. That's either filled or unfilled. Okay, the filled will be on the ground state. It's filled. Unfilled will be the what? The excited state. And then since all the state will be what? Will be compressed with each other. You see this, compressed with each other, right? There's so many here compressed each other. Eventually you see the distance, right? The distance between this state and that state gets so small, and then they become continuous, okay? When they become continuous, when they become the continuous, you can just write this like this. Because now the states are so close with each other, there's almost what? No gap between them, right? There's no gap between them. And then you see all the state will be what? Combined with each other for the band. You call that band, okay? For the conduction band, one's band, instead of the state. When you don't have many, you have still, distinguished, a separate state, you call state. Once they all come together, compress, delocalize with each other, you call that band, okay? Band. Then, since they are so close with each other, you cannot tell the difference, okay? That's called the band. Okay. So basically, there are three different ways to draw the band structures. A similar way is no, x-axis. You just see the conduction band here, valence band here. That typically a lot of people draw that way, right? And then there's x-axis. Basically, if you have a device, right? You want to start from the surface of the device. The device is metal, right? And then you have oxide. This is basically a metal oxide MOS, right? Metal oxide, MOS transistor or something like this, right? MOS, interface, okay? So MOS devices, and then here, because you start from here, can be, as this interface 0, and then goes into the semiconductor, see what the bending look like, how the electron distribution look like, and then you have this x-axis start with 0, and then that's the same thing. You can see the band structure, see EV, you see this EF, right? The EF here, this is the Feynman-Evers, and left side you see, since I have metal oxide, the metal oxide will be what? Will be band bending by itself. It's not band bending because what? Metal oxide, because typically you have what? You have like dielectric properties, right? You have, just assume, right? This all the negative here, or the positive here, right? Place. That's why the energy goes, from the left will be lower with positive holes, and the right side electron is higher. Okay, that's what you see there. And then another one, what you see will be this kind of structure. This one basically tell you the wave vector. When you think about the crystal, right? The crystal have different directions. You can have 0, 0, 1, 0, 1, 0, all these kind of different directions, right? And then on the different directions, the band structure will be different. That's how we plot it, okay? How we plot it. So this one, when we talk about the, direct band gap, indirect band gap, we use this, okay? If this, not the same key, then we call that indirect. If this have the same key, that's basically, there's no momentum change, right? And then you call that direct band gap, direct band gap semiconductors, okay? So next thing is about the, how to understand electrons. Because electrons is a major thing, right? Electron take energy from the photons, and then electron move around, right? And the electron give energy to the load, right? That's how it works. So to understand electron has both wave and particle behaviors, okay? So if the wave, you can see electron have what? Have wavelength, right? And then if you think about particles, the electron have what? Kinetic energy and then have momentum, right? So that's why it has both wave and particle properties. Okay. So the momentum typically is written as h bar k. That's h bar is h over 2 pi. Here will be 2 pi over lambda, right? This is basically the equations we also figure out what is the momentum for the electron. Okay. Then wavelength, typically lambda equal to h over p. P is the momentum. Okay. There's more things here about the electron as wave or particles. You can see when the electron, is kind of either wave or particles, you can find the probability, the electrons to stay at different state, right? And also the energy of the electrons. If you see here, if this is a band gap, if you look at here, this is the band gap. Okay, this is the EG, okay, EG, and then depends the kinetic energy. The electron stay here. Electron is is moving around, right? Electron has kinetic energy. Kinetic energy is this much, right? And then plus the band gap itself. If you assume this is energy 0, right? Is if we just assume that 0, that's a reference. Then the band gap plus what? Plus this kinetic energy. That's the energy of the electron. Okay, that's how you see that. And then if you do the second derivative of this energy over the k, or get these equations. Okay, from that equation you can find out the effective mass of these electrons. Okay, that's something you care about. You can do the same thing for hole. You can find the effective mass for hole. So that star shows that effective mass. Okay, then once we have effective mass, that's important for us because, and then we can find the the velocity, right? The velocity, that typically is the speed of electrons, right? That's equal to q times tau over m star, and then times e, multiply e. This basically, if you think about this, I think this basically is mu, the mobility, right? Q m mu e, right? That mu is mobility. Mobility is equal to q times tau over m star. That m star is the effective mass. Okay, and then the velocity will be equal to what? The tau will be the time. The a is the acceleration, right? The acceleration, right? And then is QE over m star. This is what? Acceleration, because the force multiplies the mass. This is acceleration. Acceleration times the tau tell you velocity, right? Velocity, and then that's why how you define the mu is what? Q tau over m star. Okay, these are the common equations. You can use that to figure out, what is the current density, how to find the current density, how to find the mobility, and also how to find the velocity of these electrons. Okay, any question here? If not, let's move to next slide. Tell you the effective mass actually affect the the conduction band and the valence band energy the state density. Okay, state density. That's basically the density of state called DOS or DOS. Okay, DOS, and then you can see here, if you see effective mass of electrons is typically in germanium. If you think about the density of the state, the effective mass of electron is smaller, is bigger than what? Is bigger than the effective mass of what? Of hole. Okay. In silicon, it's also the same thing. Effective mass, when you calculate the density of the state, effective mass is higher. Okay. That's all of them. Except this gallium arsenide, effective mass is smaller for electron. Okay. But for this is bigger than the bottom. Okay. That's it. But when you calculate the conductivity, is opposite. Conductivity, the effective mass for germanium, for silicon, is smaller than the hole. That's why at the beginning, like last slide, when we talk about the mobility of a hole electrons, we see electron has a higher mobility. Right? That's basically tell electron higher velocity because the conductivity is higher. That's why its mass is smaller. When the mass is smaller, it's move faster. Right? That makes sense. Okay. So here shows that, if you look at the silicon, this is the lowest, conductor band is here, highest conductor band, valence band is here. See, this is the EG. That EG, they don't share the same key. Don't share the same key. That's why there's what? There's momentum conservation you have to meet, right? You have to meet because the HK is equal to momentum, right? Momentum is different for the lowest, conduction band, highest valence band. Okay. So here I think, yeah, talk about conductivity, right? This is the current, right? The current, the current equal to what? Current density equal to conductivity multiply E, right? Conductivity multiply E, right? Conductivity actually equal to this guy. This is conductivity, okay? This is conductivity, okay? So when you think about conductivity, as we just mentioned, the electron has lower mass than the hole, okay? That's why it's move faster. Okay. So here shows the electron and holes. Let's see what time now. Sure, okay. So whenever you have electron on the valence band, here it's called free electron, okay? Free electron. Whenever you have hole here, it's called free holes. See, the holes like to stay at what? Valence band. Electron like to stay on the conduction band. And then the hole and the hole on conduction band, holes on valence band, conduction, electrons on the conduction band, these are called free carriers, okay? Free carriers. That's free carriers, right? Free carriers, including both electrons and holes. Electrons and holes. With that, you can calculate, the conductivity, right? The sigma is the conductivity. That's equal to electron conductivity plus the hole conductivity, okay? This Q is elementary charge. Mu n is the electron mobility. N is the electron, concentration. That's equal to number of electrons per cubic centimeter square. Per centimeter cubic, okay? Per centimeter cubic. And then this is for the whole, elementary charge multiply the whole mobility multiply the whole concentration, okay? So this is normal conductivity for the any semiconductors. That's including silicon. But if you think about you want to measure the conductivity under thermal equilibrium, whenever you see this subscript 0, that means under thermal equilibrium, okay? Thermal equilibrium, okay? That's also the same thing, right? The electron density, right? Under thermal equilibrium, multiply the electron mobility, multiply Q. The same thing, the whole mobility, multiply the whole charge, multiply the whole concentration, okay? And then the same thing you can see, the intrinsic, right? Intrinsic. That basically means there's no doping. You have the wafer is pure silicon. There's no dopant. There's no boron. There's no phosphorus there, okay? So the Ni basically is equal to this equation, Ei minus Ec over Kt, E power that, right? And then multiply the Nc, okay? N will be opposite, Ev minus Ei over Kt. So these are the very common, equations that's important about the conductivity, electrical conductivity on the semiconductors. And here there's a definition. What is N? What is P? What is N9, P9? The NP basically is what? It's the any charge, right? NP. That can be under what bias? Under light bias, under electrical bias. But N9, P9, that means there's no bias. It's under thermal equilibrium. Okay, NIPI basically means intrinsic. Okay, don't be confused with this subscript. The subscript means something. Okay, means intrinsic means I. When it's 0 means under thermal equilibrium. When it's nothing there, it means the conductivity for any case. Okay, so here shows you can see there's first term for electron, second term for hole. Typically, if you have if the N-type dope, this one will be dominant, right? Yeah, this dominant. If the P-type doped, then you cancel what? You go opposite. P-type, since this P is much bigger. Typically, P-type, let's see, powers 10 per centimeter cubic. That's for electron, for hole, and then the electron will be only 10 power 4, right? Because Ni square, remember Ni square equal to N9 P9, right? If the N9 is 10 power 16, P9 will be equal to what? 10 power 4, okay? Now, if this one is 10 power 4, this 10 power 16, you can cancel this easily, right? And then only the first term or second term stay, right? So, okay. So that's why it's P-type silicon goes opposite, right? P-type silicon, you have what? You have a lot of P, right? P is huge. This guy is minor. Okay, and then you can get rid of that, become Q mu P P. Okay, that will be the second term. Okay, P type the second term. Okay, if N type will be the first term. So that's a okay. That's about that. And then let's talk about the intrinsic thermal equilibrium. Intrinsic basically means I, right? Intrinsic basically when you have silicon wafers, right? Silicon wafers without any dopant, okay? Without any dopant, no N and P there, okay? No boron, no phosphorus, okay? Thermal equilibrium basically without any optical illumination, electric bias, or any other bias, right? Yesterday we talked about bias, right? You can add in the optical bias, that's where they put light shine on the device. At the electric bias, basically add voltage there, right? When you don't have any bias, either from electrical or from optical or magnetic, and then that's called thermal equilibrium. Okay, so thermal equilibrium. Under thermal equilibrium, Ni squared equal to N9 P9. Okay, N9 P9. Okay, but if it's not under thermal equilibrium, then this equation will not exist. Doesn't this equation is not valid? Okay, it's not valid. Okay, this is probably don't go, we're not talking about this. You can do this by yourself, right? Time. Now let's see if I can show a demo here. Okay, demo for intrinsic carrier density. Okay, look like I cannot open. We can do what I can do. I can restart the program. Kind of stuck there. I should just close the. Okay, the PowerPoint will be closed, and I'm going to reshare that. Okay. Yeah, it's here, right? It's here, and then we go to this website. I will show you the intrinsic carrier concentration. Okay, that's okay. Now let me share the screen for you. Okay. Okay. If you look at this screen, you see here. If I start, right? If I start, say this intrinsic carrier concentration. Intrinsic carrier concentration. Okay. Now let's see in semiconductors, there are two different temperatures, right? Okay. First, let's start. Okay. At absolute zero temperature, what will happen? Absolute zero, there's no what? Right? If, that okay. At absolute zero temperature, there's no electron hole, right? But this one is a little bit higher temperature. This is elevated temperature, okay? And then now let's see if the temperature get even higher. You see that you have more charge, right? If you go back, this is when the temperature is a little bit, higher than the absolute zero, you have a few carriers, 1 or 2 carriers of fuel, right? When the temperature is high, you'll be able to create, uh, when the temperature high, you'll be able to get many more. Okay. Okay. This absolute zero, the number of carriers has sufficient energy to transfer from one band to conduction band. Nothing. Temperature a little bit higher, see this. When the temperature is much higher, you will see more, one or more of the electrons will be on the conduction band, and the hole on the valence band, they will more. Okay, that's what it means. Okay, now let me go back to my slides. Stop sharing. Slides here. Okay, this is what I just showed you that. the temperature actually affect how much intrinsic carrier, okay? As room temperature, you have about 10 power 10, okay? Electron and holes in these pure silicon wafers, okay? Per centimeter cubic, that's what you see there, okay? And then under semi-equilibrium, that's basically whenever we see N9, P9, that's a doped, right? Doped. Doped N9 multiplied P9 equal to Ni squared, okay? For example, okay, the Ni is always, it's always this, right? As I just mentioned, right? Ni is intrinsic, it's always like that, okay? If you know N9, you can find P9 equal to Ni squared, N9. If you know P9, N9 will be equal to Ni squared over P9. You see that? That's what you saw. And then typically this N9 or P9 depend. If this is a N-type doping, that P9 is equal to Na. Na is acceptor. How much acceptor? The acceptor basically here is boron, right? How much what is concentration of boron you doped in these silicon wafers? And then if it's P-type, that will be dollar, right? P-type, the silicon wafer get extra electrons. Someone give him, right? That's phosphorus, right? The dopant of the dopant phosphorus concentration, that's Nd. Then you can replace Nd, replace N9 by Nd, replace the what P9 by what? By Na, right? And by Na. That's what you see there. So this is very important equations, okay? To figure out if you know the dopant concentration for acceptor, you can figure out, how many electrons there, how many holes there. If the dopant concentration is what? Is holes, you can figure out how much electrons you have there, okay? So this is another video I think I can show you here is a cartoon. This shows the under thermal equilibrium, okay? Thermal equilibrium. Okay, this is the equation we just talked about. Oh, now let's see, okay? Stop. You see, this is intrinsic, right? Read here. Intrinsic materials have equal number of electron holes, right? Equal number of electrons in the conduction band and then equal number of holes on the valence band, okay? Now let's see next, okay? When you dope this with electrons, if this is N-type dope, now you see how many electrons you have the conduction band. Only a small amount of holes on the valence band because N9 multiplied P9 equal is constant, right? If you have more here, electrons, N9, you have much less on the P9 because N9 times P9 equal to what? Constant, right? So that's what it means. Okay. Next, now, if that concentration, you get even higher, and then eventually you get much less, much fewer holes there. That's what it means. Okay. Is that clear for you guys? Okay. That's why it's N9 P9 is N9 multiplied P9 is constant.
Sir, we cannot hear you, sir. You are muted, sir.
Yeah, I just accidentally click on the mute. Okay. So now you can see the website, right? When my dopant concentration, for example, Nd dollar, right? The phosphorus has more that basically bring more electrons to the wafer. That's why you have more electrons on the conduction band, less on what? On the valence band. Now, if you increase that dollar concentrations, you will increase even much more, electrons in the conduction band, and then reduce amount of holes on the valence band. Okay, that's what it means. Now let me go back to my slides. That's what it means about N9 P9 multiplied, a product of N9 P9 is constant. Okay. So with this, these are some questions you guys can figure out by yourself. Very simple calculations. Okay, the same. Okay, I'm gonna skip this. And then, since you guys, this is about photovoltaic, right? Also, the organic solar cells always has something called excitance, right? And also there's polarance, okay? So the excitance basically in organic materials, right? If the electron hole are generated by night illumination, you generate electron hole, but they still the bond with each other, okay? They're called excitant. You need energy to dissociate that excitant, okay? And then right after the excitant, dissociation, you'll form separate electron holes, and then that electron hole is called polarance, okay? Called polarance. So that's polarance because the interaction between the electron or holes and that between electrons and the lattice, or between holes and lattice, are so strong that electron will be, cause local distortion in the lattice. Then you call that polarance, okay? I used to teach, another class called organic solar cells. I'm not sure in the future, maybe you guys interested at that class. Organic solar cells, we do talk a lot about excitance or the polarance there. So I think this is the energy level diagrams. We talked about this before. I don't want to repeat this, right? And okay, another thing is important for solar cells, especially the light absorption, right? You think about solar cells, you put the solar panel under sunlight, it has to absorb the sunlight, okay? If you think about the absorption, optical absorption in the solid, there are 5 different types. The first one you can call free carrier absorptions, okay? Free carrier absorptions. The second one called phonon absorptions, okay? And then the third one is called electron interband transition, okay? So let me focus more on the interband absorption. So what is interband absorption? If you think about, if you call this CB, 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 okay. There's a band, this is conduction band, this is valence band. The interband basically involves 2 bands, right? If the photons comes and promote electron to there, or stay here, and then you call this one is interband, okay? Interband transition, interband absorption, okay? And then there's other type, this is basically 4 here. You have interband absorption, but you generate electrons here, hole is here, electron here, hole is. Then these 2 are bounded with each other. That's called excitant, okay? And then you generate electron hole, but you did not generate the free electron hole. You generate electron hole pair, okay? That's the process 4. And then the process 5 is amorphous materials. This is the hopping of electrons from look-like state. Because if you think about amorphous materials, you don't have band. You have a lot of state like this, right? Now this for what? HOMO. HOMO will be the same thing here. Oh, sorry. State. Separate state. This. This. You see the electron state here will be hopping like this, hopping like that, okay? That one is number 5. There's some hopping inside the band. And then the first one, free electron absorption, if you think about this in a band, okay, from a state to another state. For example, right? Same thing here, that's all. As we discussed earlier, right? We call this band, right? We call this band, right? We call it band, but actually there's a state in between, right? There's state in between. There's state in between. Okay, inside the state, the electron goes from here to there. That's called free carriers absorption, right? Because this is CB, conduction band, or free carrier, right? Free carrier absorbs some energy, promote itself to, the next energy level. And then phonon absorber will be the same thing. Maybe not only one, will be quite a few of these. And then you see it's absorbed the thermal energy, promotes itself. This is very similar to that. Okay? But what do we care about this optical absorption? Whenever you talk about something like this, 1, 2, 4, 5, these are basically infrared or near infrared, okay? Infrared, far, mid, or near infrared, absorption. Only this number 3 is visible light absorption, okay? That's the major portion for the solar cells light absorption, okay? Here there are more, introduction, more discussion of this. I'm not going to spend time here. You guys can read this. And here there shows, ask you what is the measure, photon absorption in solar cells. That's what? Interband, right? Interband transition, because you promote electron from valence band to the conduction band. Okay, that's the most important for the light absorption, right? And then here, the question about, which one has the smallest momentum, right? If you think about momentum, the momentum equation equal to h over lambda, right? Lambda is what? Lambda is the wavelength, right? Think about the wavelength for what? Photon is the visible light. Just give example, 500 nanometers. For electrons is 1.23, right? And then for photons, it's also, somewhere between one at different temperatures, the photon wavelength is different, right? Higher temperature, that wavelength maybe here, the wavelength actually get longer, right? So overall, if you think about the h divided by lambda, which lambda is smallest, right? Electrons is smallest, right? That's why electron has the highest momentum, right? If you think about which one has smallest momentum, that's what? Photon, right? The photon momentum is so small there, okay? Photon so small that you can ignore it, right? That'd be A, right? Is the answer, okay? So the next thing, actually explain, what is momentum photons, photons, is pretty small because what? Because the wavelength is so big, right? But compared to electrons, right? That's pretty big, right? Okay. So here shows basically the, something called momentum conservation. Momentum conservation. So basically, if you think about here, if you have electron promote from here to there, this is key, right? Momentum is what? Momentum is h key, right? H bar key, P equal to h bar key. Okay, h bar key. If this key is the same location for the transition from here to there, the same key. Here to there, the same key, same key, same key. And then you call this, the key is reserved, right? The key is the same. You have this momentum conservation, right? But now if you shift it, right? If you shift to the right side, now initially this my momentum is h1 bar kv. Now my momentum become h bar k1 kc. Now the kv kc are not the same. Now see, my electron has a momentum before I do the excitation is here, is kv. Now I feel my what? My excitation, and then my momentum, kc, they're not the same. And then you have to, conserve the momentum difference. And then that way you have to involve a phonon, right? Phonon. To involve phonons, right? That's why phonons is involved to keep the momentum the same. And then that's why this called indirect band gap. Okay, band gap. The indirect band gap has a lower light absorption because it involves, phonon absorption involves the momentum. Okay. So this is okay. I think I have applied about what 9 minutes left. We can either, I have probably a lot of more slides. I think this there's a lot of important information about the physics. I think tomorrow we have the tutoring, right? Probably I can use the tutoring to continue the lectures, right? And then, because this chapter is so important, I don't want to miss anything here. Let me continue, a few more slides, and I'm going to take some questions. And the remaining slides, I can talk about this on tomorrow's lectures, okay? So that's what we discussed, what is the direct band gap, what is the indirect band gap, and the next thing will be what? Either direct or indirect, how can I determine my absorption coefficient, right? The absorption coefficient, basically, the high absorption coefficient alpha, right? This one is alpha. When the alpha gets bigger, that means I have a thin film can absorb a lot of photons because my absorption coefficient is so high. I have so strong absorption capability. Okay, that alpha absorption coefficient means that. So what determines that absorption coefficient? That basically you need to have sufficient number of what state. What do you have there? First, you can see it this way. You can see GV, GC. What is GV, GC there? Let me just remove this so you can GV, GC. right? So where's okay, the density. Okay, that's the phonon. So we don't talk about that. Okay, let's see here. Density of available electrons. This one is the available electrons on the here. How many electrons here? Okay, and then how many holes, right? This one you can density available empty state. So whenever you think about you promote anything from here to there, you promote electrons there, there's a hole behind, right? So basically, after you did the promotion, how many holes you can hold here, how many electrons you can hold here, that determine how many, light absorption you can have, right? Without this number of electrons, without this number of holes, this H mu will not be absorbed, right? Whenever they absorb this H mu, you have to have that many number of electrons on the conductor band, that many number of holes on the valence band, because that's what happened after the photon absorption, right? So that's why the number of these, the density of available uh, electrons or electron state, that's the same thing on the conductor band, or density of this whole state on the valence band. And also the probability for them to meet each other, right? Then that's the P means the probability for them to meet each other. You can call that, cross section, probability cross section. That's basically, when one electron, what is the chance for it to meet that hole? Okay, so that's why P probability, right? And then multiply the density, the density of the state for electron, the density of state for holes, and also this is available of electrons. You have to have electrons there, not the empty state. Empty state doesn't have. So basically, you can see the density of electrons on the conductor band, the density of holes on the valence band. Okay, and then multiply the probability for them to meet each other. That's how you figure out, how to figure out the absorption coefficient. Okay, so yeah, so here shows the absorption coefficient. You can use this equation. It's a pretty complicated equation. Figure out how to calculate that absorption coefficient. Because here, you see here, they have the same key, same momentum, right? Same momentum, h bar key, right? And then you know that, they are what? This direct band gap, okay? If this shift to the right side, and then that's called indirect, okay? Indirect, you have to involve phonons. The phonon can either, the phonon can be, you think about that, right? The light absorption, you can emit solar energy, right, to outside. Or you can also absorb the solar energy from the environment, right? When the when the electron promote from ground state to excited state, they either release solar energy to the environment, or they can absorb energy from the environment. That depends, how much the photon energy you have, okay? Or the energy will be from the photon energy, okay? If the photon energy is bigger than the band gap plus the photon energy, you have both. You can absorb the solar energy, also release solar energy. That's why you have both, right? This one, actually, your photon energy, right? And this is the EP plus that. This actually is the photon absorption, and then this one is the photon emission. Okay, because EP minus that, right? You have too many EP, you emit that. So that means when you have a lot of photon energy is large enough, you can have both. That's why the coefficient include both. You both emit photons or absorb photons. But when the photon energy is smaller than the energy, your emit photon energies, right? And then you only have this what? Absorption. You can only absorb the photon energy, right? If this energy is smaller, the photon energy is even smaller than this, the band gap plus the photon energy, you steer the photon energy is not enough, and then you have your light absorption does not happen, right? Because the photon energy does not provide enough, and then plus the environment solar energy, that still not enough to promote electrons. That's why there's no absorption. Okay, this is about that's why for indirect band gap it's pretty complicated. Okay, I think this is good enough. Probably next tomorrow morning we're going to continue these lectures. Okay, let's try to use some tutoring time to complete this slide. So what we can do, we can continue, about another 20 slides. Maybe I can select some slides to present, and then we can continue to the next lectures. Okay, right now I think I can stop here. Okay, and take any questions. Let's spend a few minutes to take questions.
Thank you, sir, for such a nice lecture.
Thank you.
Participants, if you guys have any question, you can raise your hand.
Or maybe they have class after this, right? Because this is daytime, right? So it's not like at night. So if that's the case, you can save the questions for tomorrow. That's fine.
Yes, sir, that would be better because they can ask question in the tutorial session also.
Yeah, yeah. You can ask question anytime. We have 2 hours.
Yes, sir, because as of now, I cannot see any question in the chat box as well. Yes,
Yeah.
sir. Syed Ansari has raised his hand. One, just a second. Let me.
Okay, okay, that's good. Okay. So we'll see you
Uh,
tomorrow. No, not tomorrow, this evening, right? For you guys.
yes, sir.
Okay, great, great. So yeah. Okay. Then okay,
Okay, sir.
see you guys.
Thank you, sir. Thank you, sir.
Good morning. Bye-bye. Yeah.
Yes, sir.
Thank you, Professor Chow.
Okay, no problem. Thank you, Mohesh.
Thank you.
Cat,
Thank you.
right? Mohesh. Thank you, Nipam, right? Thank you, Ahmed is there too. Okay. Okay, bye-bye.
Thank
Yeah,
you, sir.
see you.
Participants, we'll share the lecture slides with you in few hours. You can save your question and can ask in the tutorial session, which will be from 7:30 to 9:30 in the evening. So till then, goodbye.